Hey guys, good morning. Hope you all had a good weekend. Um, had a good Mother's Day. Hope you're all able to contact your families. And um, Administratively today, I don't have much. Homeworks are due tomorrow. Homework threes are due tomorrow. This morning, we'll do a homework Q&A for questions about that. And today I'm going to move on from ceramics. That was just a short one-day lecture, and move on to polymers, chapter 14. My note set is together on polymers, both chapter 14 and 15. And unlike the ceramics unit, I'm actually going to break that into two videos. So this one will probably be a little bit shorter, which is okay because I've been running long. And so I'm going to go ahead and do the normal thing. We'll switch over here and share the notes. These are already up on Teams. Okay. So polymers is the third class of materials that we are looking at in more depth. We started with metals, and the focus of our time will end up being metals. We will have spent more time on that than any others, but I think it's instructive to talk about the other class of materials, both for your introduction if you're relatively new to material science, and also as by way of reinforcing kind of the main points, because in a lot of ways we'll look at the same types of things that we did with metals, but the different classes of materials obviously have different properties with respect to those same factors, and so and of course polymers, ceramics, while we don't make aircraft and spacecraft solely out of these materials or even primarily out of these materials, they still have application. Okay, and so to kind of start at the beginning, this first chapter will be about polymer structure, and then chapter 15 is about applications and processing, similar to the model that Callister has adopted for previous materials. And we'll be focusing on synthetic polymers. Synthetic polymers really became about as a result of the boom in manufacturing after World War II, and the drive to develop a lot of them synthetic rubbers and other polymers came from the need for to produce them for the war effort, specifically synthetic rubbers, because the natural rubbers from plantations in the Far East, right, were cut off by the invasion of Japan, and so they developed the synthetic replacements. And this is to differentiate between natural polymers. So silk and cellulose and wood have similar chemical structures to what we look at in synthetic polymers, long carbon chains, as we'll talk about, right? But they're naturally produced, and we have less control over their properties as a result. From a bonding perspective, hydrocarbons, well, polymers are basically hydrocarbons, and they have two types of bonding. Intramolecular, meaning between atoms in one molecule, you have covalent bonds. You have electron sharing between carbon atoms. So carbon is group 4, if you remember, sp3 hybridized bonds, so it can form 4 equal bonds, and has 4 electrons to participate in covalent bonding sharing. Hydrogen has just 1, and so you can produce a long carbon chain, and each of these carbons will have 2 electrons left over for additional bonding, and they satisfy those with hydrogen. So there's covalent bonding within the chain, and then in between chains, there's no permanent bond. Instead, we only have weak intermolecular bonds, right? Van der Waals. If you recall, van der Waals are due to instantaneous dipoles. And so carbon and hydrogen, neither one of those is particularly electronegative, and so it's not a highly polar bond. And but there's a probability that there'll be a distribution of electron charge that could produce positive and negative, kind of momentary imbalances, which will provide a weak attractive force to these induced dipoles. And so the weak intermolecular bonding between adjacent hydrocarbons is the reason that small hydrocarbon molecules tend to have very low boiling points. Methane is a gas at room temperature and doesn't liquefy until 164 degrees Celsius, negative 164 degrees Celsius. And we see here that as we add carbons to form a carbon chain, right, as we go from 1 carbon to 2 to 3 to 4 to 5 to 6, we see that the boiling point quickly increases until we have here, with only 6 carbons, a hydrocarbon that is liquid at room temperature. And the reason for this is that these van der Waals intermolecular bonds are additive. So as we're adding more carbons in the chain, we have more opportunity for the van der Waal forces to develop and to attract neighboring molecules to one another. And so this chart stops at hexane, but if we were to continue to go up, we would see that the boiling point would continue to rise. We would transition from liquids to thicker, higher boiling point hydrocarbons, eventually transition into waxes, and if you continue that to its logical end, you end up with a solid material, which is essentially what we have for a polymer. We have a long carbon chain that becomes so long that the chains, despite having weak bonds, there are just so many of them, and they're so intertwined with one another that we end up with a solid material. You can think very much of a polymer like a chain. You have a carbon chain, but you also have a chain of individual repeating units. And so I believe the Greek here, so mono is one, mer is part. So monomer is one part. And if you link together many monomers, you get a polymer. So you have many parts. And so you get a polymer just by linking together many of these monomers. And we'll talk a little bit about different kind of chemistry reactions, I think later on, maybe on the next page here. But here's an example of the polymerization of ethylene. So F is the prefix for 2 carbons. So you get 2 carbons, and then the ylene part refers to this double bond. And so so you have this molecule, and this particular polymerization is produced by an initiation or catalyst. So you have a molecule here represented with R that could be, is much larger. It's not, we're not talking about, one atom here. But the defining factor is that it has what's called a free radical, which is an unpaired electron. And so that electron's unpaired, it wants to find a pair. And this double bond is a good place for it to scavenge that extra electron. And so it attacks that double bond and forms a single bond between your initiation molecule and your um, ethene molecule. And so that leaves another free electron, right? So I've broken this one of these bonds. One of those electrons forms a bond with this existing free radical and leaves me a free radical. So this becomes now the next place where we extend our chain, right? So then we have this free radical come and find another ethene molecule, break open this bond, and add it to the chain, right? And so that continues to occur until the chain either becomes immobile because it's been tangled up with many other chains, or we have run out of monomer. And so it can happen many, many times, giving us a very long chain. And the degree to which that polymerization, and I should probably mention here, so here we have ethene, right, where we have two carbons with a double bond and all hydrogen, but we could just as easily swap out these hydrogens for other atoms, right? If you put a fluorine there, you put 4 fluorines or chlorines or a methyl group, a CH3, right, or a benzene ring. That's essentially gives you many different polymers, right? So it kind of, whatever you specify as the monomer basically becomes your polymer, and you can swap out for these side groups pretty much many different other chemistries. Okay, and so this polymerization is a bit probabilistic in the sense that you are going to run out of monomer at different numbers of monomer units, right? So this N is an integer for a particular carbon chain, but it is not always the same N, which gives you a distribution of molecular weights. And so you can characterize the size of your polymer chains in a couple different ways. The two of the more common ones are a number average, right? So this would be looking at each polymer chain in terms of the number of monomers, perhaps. Or I guess it would be the number of chains of that length, right? So here I'm plotting the amount of polymer versus molecular weight, and so I have the most number of chains of a certain length. But if I consider the weight of each one and don't just count them as an individual chain, but I take the average weight of all of them together, I see here that my distribution is not symmetrical, right? So the number average, it's not a bell curve, the number average is not the same. I'm skewed towards higher weight molecular chains. Even though there are fewer of them, they are heavier, and so that tends to skew my weight average to a higher value than the number average. But this is an important, the characteristics of my polymer are important in the sense that I have an average weight and then also a distribution, right? So the width of this distribution is important when considering the type of polymer that I have. In general, the polymer chains are very long, so we're talking about hundreds of monomers with thousands or tens or hundreds of thousands of grams per mole for these molecules. Like I said, they're not all the same because we have different distribution of lengths, but we're always going to have an integer number of monomers, right? We're going to be adding these monomers one at a time, and we're not going to add an arbitrary number of atoms, right? It's always going to be the same link in the chain, so to speak. And like we saw here with the simple hydrocarbons, the polymer chain length affects its thermal properties, specifically its melting temperature. So like we saw here, as we had a longer chain in our hydrocarbon, we had a higher boiling point. For for polymers, longer chain length increases the melting temperature also, less dramatically than what we have here, but nevertheless. We also don't have straight polymer chains. For one thing, certainly not straight in the sense of this diagram. We remember that that sp3 hybridized atoms, group 4 atoms, they want to have these bonds spaced as far apart as possible. And in a three-dimensional sense, you can do a whole lot better than the 90 degrees that you would see kind of in a plane. And what happens actually is that they actually have a bond angle of about, not 90, but about, I think, 109 degrees. And you have a bend sort of in one plane, and then the other 4 atoms, the other 2 atoms, excuse me, have a similar angle, but in a perpendicular plane. So even if you were to stretch out a polymer chain as straight as possible, you would still have this kind of zigzag pattern with your hydrocarbons in a totally different perpendicular plane. But you don't have this, typically is not even, you don't have chains that are as straight as this, because these single bonds do not restrict the rotation of the atoms around them. And so you can have bends and twists and kinks in your polymer chains because these single bonds are free to rotate. And so what you end up with, and the kind of the mental picture that I like to think about, is that a polymer material has many chains, and they're all twisted and kinked and intertwined with one another, that you can kind of think about it on a molecular level as like a plate of cooked spaghetti, or like a tangled fishing line. And you know, one polymer chain might be something like this, right, where you have, you know, this is the distance between the ends here, but in between there you have any number of bends and twists and curves, and it bends back on itself, and you can picture this as just one chain, and then intermixed with this would be, you know, many other chains forming a solid material. So it really is, you know, kind of an intermixed, and you know, a plate of cooked spaghetti is probably, you know, kind of a simplified, you know, relatively orderly a way of thinking about it. But as we'll see later with the applications, this gives you a lot of space to deform and to potentially stretch out. So when we talk about the mechanical properties of polymers, right, having this picture here of this tangled up fishing line and thinking about it stretching out or deforming or crystallizing might be this may be a helpful mental model to kind of keep in mind. From a molecular structure standpoint, we have a couple of main categories. The first is the general chain geometry, I guess. You can have a linear or a branched polymer chain. Now, a linear is going to form from a simple polymerization, say here from ethene, right? So here, there's really only one direction that it continued to polymerize, and there's no side groups that can participate, and so you get nothing but a long linear chain here. But if you had a more complex monomer, say that you had 2 double bonds, then you could potentially polymerize in more than one direction, and that would produce a branched polymer chain, where you would have these branches and these kind of side lobes, I suppose. And while talking about this, you could also, if you were to swap out these hydrogens for larger subgroups, you could have, you know, kind of somewhere in between where you have a linear chain, but you have these side groups that are distributed along that chain, not a separate chain, but just you know, giving more structure to the linear chain, and this has property implications as well. Another key distinction is whether or not the polymer chains can react with one another and form what we call crosslinks. And this is the key difference between later when we talk about thermoplastic versus thermoset polymers. The linear and the branched are in the class of thermoplastic in the sense that these polymer chains are not bonded to one another. And so if you can increase the temperature of the material enough, they can move with respect to one another and slide and melt. But if you were to have monomers that could react with an adjacent polymer chain, then you have a rigid network. And so these adjacent polymer chains can no longer slide with one another because you might be able to overcome the weak van der Waals attractions with increasing the thermal energy of the system, but the covalent bonding present with these crosslinks is much stronger, and by the time you can break these bonds, you're also breaking these bonds in the chain. And so what you get is not a melting, but a disintegration of the entire material kind of at the same time. And so thermosets here, this is a result of a chemical reaction forming these crosslinks, and thermoplastics, these can be formed and reformed just with the application of heat. And also from a molecular standpoint, you have structure within the chain, have it with regards to how the potential side groups are arranged. You can have a conformation here. So if you have a double bond within your chain, those double bonds are not free to rotate like single bonds are, and so you have to make a choice when you're going across the single bond. Say, here's the polymer chain going from this carbon to this carbon across the double bond and then back down. So since it's rigid, you can have the carbon chain kind of stay on one side of this bond. This would be the cis configuration, or you can have it go to opposite sides of the bonds. This would be the trans configuration. And you can also have different arrangements of the side groups. So I mentioned up here that you could swap out hydrogens for other side groups, and they could be quite large. And so if you have large side groups, they need to arrange themselves also. And there's different ways that they can arrange themselves. There is isotactic, where you would have all of the side groups on the same side of the polymer chain, or I think syndiotactic, where you kind of have this alternating pattern, or atactic, which is random. And the stereoisomer that forms here has implications, as we'll see later on, for how a particular polymer may crystallize. You can imagine if I have an orderly pattern of how these side groups are arranged, it would be easier to align these polymer chains in an orderly way and form a crystalline region. Okay. I just talked about this on the previous page. You have thermoplastic versus thermoset. The cross-linking is the key there, but from a processing standpoint, the big difference here is that thermoplastics soften when heated, harden when cooled. This is a reversible reaction. So I can soften and reform a thermoplastic polymer potentially indefinitely, but a thermoset is made via a chemical reaction. So this is what you might see with like a two-part epoxy, where you get you're adding part A and part B, and they chemically cure and form these crosslinks. And a thermoset is non-recyclable, right? So if you try to heat that up, like I said before, you'll just burn it up. it will never soften. However, but it also results in a much stiffer final product. Okay, so in addition to the structure of an individual monomer and how the side groups are arranged, we talked about stereoisomers on the previous page, you also have different ways of arranging the particular monomers. Now, if you only have one kind of monomer, there's really nothing you can do. But you could have what's called a copolymer, which is a collection of different types of monomer links. And they can be arranged in different ways, which gives you, different polymer chains and polymer structures. So you could have a mixture of multiple monomers that bond in a random pattern, right? That maybe be something like this. You could have the chemistry such that they alternate, or that they, that the reaction proceeds in stages where you polymerize one and then the other, and then polymerize them together to form a block copolymer. Or you could have this grafted arrangement, which is called a graft. I think borrowing a term from gardening, where you would graft one type of branch into another type of stem. But here you would have one type of polymer kind of branching off of another in a grafting kind of way. And you might create a copolymer, right? It's sort of we'll talk about composites in a few lectures, but this is sort of kind of a molecular composite of sorts, where you are picking different monomers that form different polymers and combining them together to get kind of a hybrid polymer with desirable properties, right? So this is, if you've ever heard of ABS, right? The A is acrylonitrile, the B is butadiene, and the S is styrene. These are three different polymers that are combined together. Okay. And so I think the last big topic is crystallinity. And so it might seem counterintuitive if you have this mental model that you have these tangled polymer chains and this kind of random plate of spaghetti kind of model, that you would have a crystal, but you can, and you get that by orderly packing those molecular chains in together. And the picture there, if you're thinking about a plate of spaghetti as polymer chains, I would think, I would encourage you to think about the crystalline regions maybe as the spaghetti while it's still in the box, right? So here we have the polymer chains, packed in closely to one another with a high degree of order, and forming a crystal. Here, there's a couple distinctions between, the differences between what we talked about with metal crystals, in that, a polymer crystal is never going to be 100% crystalline, because you've got these long chains, and there will be regions where you have amorphous chains, and you really can't get around it. And generally, what you see is crystalline regions that are connected to one another with amorphous regions. As you might expect, when you have a crystalline polymer, the density is higher. Crystals form kind of at the optimal arrangement of a particular unit, and so if you have a crystalline region, then you can pack it more densely. It's also typical of crystals, as we've seen before, is that materials crystallize when they are allowed to form slowly. And so just like other material systems, crystalline polymers are formed under a slow cool. So you need time, but you also need temperature to enable those atoms to be mobile enough to form crystalline regions. And it's easier for so some polymers crystallize better and easier than others. And if you, think back to our polymer chain picture, you can imagine a simple polymer chain like polyethylene, which is just a straight carbon chain with hydrogen side groups, it would be much easier for these chains to tuck in next to one another and form a crystalline region. You can imagine the difficulty in crystallizing a polymer if you had a large subgroup hanging off the side getting in the way, and those subgroups were in the polymer in a random pattern. So you're going to get a better, higher crystallinity material if you have simple linear or orderly polymers with small side groups. So if you were to have, go back to those stereoisomers, right? If I were to have a large side lobe here in an atactic isomer, right, it would be very difficult to tuck those in and form a crystalline region. Okay, so if we have crystals, the next thing to talk about is crystal defects. And here the crystal is a little bit different, and so are the defects. We're forming defects by having chains wrap back and forth and lay in an orderly pattern next to one another. And so this can occur, but let's remember that these are chains, and the chains eventually end, right? So we have defects that are related to having part of the chain kind of hanging off one side of the crystal, or having a tangle, a non-crystalline region kind of within the crystal, right? Or a loop of chain, or an end of a chain and then a new one. So there are most of the defects that you can think of occur from the fact that we have a polymer chain that is being, basically kind of looped back and forth to create a crystal. And you can get, so when you form a crystal on a kind of a macromolecular scale, they fold up in two main ways. One is to form kind of a platelet where you have this relatively thin region here where a single polymer chain is able to fold back and forth on itself. They also have the formation of what are called spherulites, and they're called spherulites because of their spherical nature. And here, this should look very similar to the nucleation and growth of crystals on, in a metal system, where you have a nucleation site where you start to get your molecular chains crystallizing, and it essentially grows out from there, similar to what you would think about with a grain boundary growing. But here, the polymer chain nature comes back and exerts its influence in that you don't have a continuous crystal emanating out from this point, but you have regions of crystalline behavior with amorphous regions in between, and it grows out and forms this spherulite emanating from this nucleation site. Okay. And as has been a common theme here, we have a lot of the same phenomena in polymers that we do with metals. It's just with a twist because of their particular chemistry. Diffusion is no different here. We have diffusion in polymer systems, but generally you don't think about their elements diffusing. Rather, you think about other molecules diffusing in them. So the polymer becomes kind of just the solvent, and the solute would be other molecules. And this is because generally these chains are so long and intertwined that they're not mobile, right? They're not going to be diffusing in the material because they're so long, they're so intertwined, they're not going anywhere. But you can diffuse, say, a small solvent molecule, like a solvent is like an organic solvent, like acetone or alcohol or water. Those small molecules can dissolve into the polymer structure, and this is what we think about, with maybe dissolving a polymer resin, is that you work those solvent molecules, diffuse them into the material, and it pushes apart the particular chains, and then can put them, moving them apart enough that they become soft or even form a solution. You would have a greater diffusion rate, obviously, in regions where there's more space, right? This would be similar to the fact that you have faster diffusion along grain boundaries in metals than you would in the bulk crystal here. You're going to have greater diffusion in the amorphous polymer regions than you will in the crystalline polymer regions, just because there's more space in between those chains than if they're packed in tightly against one another. And if your molecule that's diffusing through a material is small, it's obviously going to diffuse faster. This would be analogous to what we saw with the diffusion rates of carbon versus iron in an iron crystal. And also if they're inert. So if you have a highly polar molecule, chances are good that it could be attracted to one part of the polymer structure, say a side group with a polar bond in it or something, in which case that attraction is going to slow down that diffusion, right? But if it's inert, then it's not going to be attracted to any part of the polymer structure and is going to move through it more rapidly. And so this diffusion, since we're talking about molecules diffusing through the crystal rather than atoms of the crystal itself diffusing, we think about it not so much as a diffusion coefficient, but we talk about it in terms of it being permeable, right? Having those smaller molecules able to permeate through the material, and this gives rise to this permeability coefficient, which should look similar to Fick's first law, in that we have kind of a constant, I guess maybe P sub m is the permeability coefficient, but the flux through the material due to this permeability coefficient, right, would be dependent upon, what's delta P? I forget what delta P is. I'm going to have to come back for this, talk about that for the next video. But this is analogous to the concentration gradient that you would see in traditional Fick's first law. Okay, so that pretty much wraps up chapter 14 on polymer structure. And I think this video is a bit shorter, so we'll pick up with the second half of this note set tomorrow and talk about the polymer characteristics. It will be very similar to what we talked about today in sort of rehashing a lot of the same ideas, but in the context of polymers rather than metal systems. So until tomorrow, and actually here in a bit, I'll be on Teams for a homework Q&A. All right, see you tomorrow.